Imagine opening your eyes to the night and being told that everything you believe about where you come from is a comforting lie. Picture a reality where your veins carry not the oceans of Earth but the dust of another world, where the cradle that bore your ancestors was not a green and blue sphere but a small red dot glinting in the void. Visualize a single rock, older than any human memory, streaking through space, carrying with it the first whispers of life across a gulf of emptiness. What if the story of life on Earth began not in its oceans but in a place shrouded in rust, dried up riverbeds and frozen lakes? And what if we are all Martians without knowing it? The notion sounds like the fever dream of a recluse, a conspiracy whispered in dark bars, a tabloid headline gone mad. Yet somewhere deep within your mind, a voice asks, what if it is true? There are those who cling to tales of ancient beings descending from the sky, of secret experiments conducted by beings from distant stars, of civilizations wiped away by cosmic disasters. They tell stories of human genes manipulated in the red sands, of messages carved into pyramids, of prophecies hidden in the patterns of stars. They point to the meteorites that occasionally crash onto our planet as evidence that we have been visited, that our DNA is an alien signature. These ideas are seductive because they offer a grand narrative, that our existence is the outcome of deliberate cosmic art. Such thoughts tickle the part of our brain that longs to be special, to be chosen. Welcome to Deep Space Secrets. Turn down the lights, let the glow of your screen be your only star, and settle in. If you have not already, subscribe and join this journey into the unknown. Take a deep breath and allow the questions that disturb your sleep to drift into focus. Together we will travel to the edge of our understanding and peer into the abyss between myth and reality. Our ride begins with the wild theory that life on Earth was planted deliberately by intelligent beings, or at least by the indifferent hand of cosmic accident. The Panspermia hypothesis, from the Greek words for all seeds, proposes that life did not originate on this planet at all, but that the universe is full of microscopic life, and that some of it drifted or was hurled through space to land on hospitable worlds. There are two main versions. One is natural, with comets and meteorites acting like ships. The other is directed, with advanced civilizations seeding planets intentionally. For decades, this idea has been mocked by many scientists, yet it refuses to die because the alternatives are no less remarkable. If life can arise spontaneously from non-living matter, why could it not also travel from world to world? To those who crave a cosmic origin story, Mars is irresistible. The red planet is older in some respects. It formed alongside Earth, but its smaller size allowed it to cool quickly. While our early Earth was a seething oceanic inferno pummeled by asteroids, Mars may have enjoyed a calmer childhood. Evidence from rovers and orbiters reveals ancient riverbeds and floodplains, the ghostly fingerprint of lakes and seas. Imagine the Martian landscape billions of years ago. Thick clouds, flowing water, perhaps a gentle rain falling on iron-rich deserts. Scientists have found minerals on Mars that require long-standing water to form, and they have detected clay deposits that form in neutral pH environments suitable for life. More intriguingly, certain elements crucial for prebiotic chemistry appear to have been more abundant on Mars than on early Earth. Among the chemical ingredients thought necessary for the transition from chemistry to biology are minerals that contain boron and molybdenum. On early Earth, these minerals would have been rare because our world was a water world covered almost entirely by oceans, with only a sliver of land rising above the waves. In such a wet environment, borates dissolve and are dispersed, while molybdenum remains in an oxidation state that cannot catalyze the formation of ribose, a critical component of RNA. Mars, with its drier climates and higher oxygen levels, could concentrate these minerals in desert basins where intermittent wetting and drying cycles might have stitched together the first self-replicating molecules. The combination of boron to stabilize organic compounds and molybdenum to reshape them into ribose suggests a geochemical dance more likely to occur on Mars's surface than on a flooded early Earth. If life did arise on Mars, it would need a way to escape once conditions turned hostile. Astronomers and geologists have discovered that Mars has thrown rocks into space for as long as the solar system has existed. When a large asteroid slams into the Martian crust, fragments are blasted into orbit. Because Mars has weaker gravity than Earth, these fragments can more easily achieve escape velocity. Many of them eventually cross Earth's path and are pulled in by our planet's gravity, falling as meteorites. Hundreds of these Martian rocks have been collected in Antarctica and the Sahara. One meteorite, designated Allen Hills 84001, contained features that some researchers interpreted as fossils of ancient microbes. Controversially, the interior of that stone never heated beyond 40 degrees Celsius during its journey through space. That means that if there had been any hardy microbes within its pores, they would not have been incinerated. The idea that life could ride a stone across space, frozen yet viable, starts to feel less like fantasy and more like possibility. If tomorrow you learned with certainty that your ancestors were born under a different sky, would that knowledge change how you love this world? Tell me in the comments. The roller coaster now plunges into the abyss of critical thinking. While the Panspermia hypothesis is fascinating, it demands that we examine harsh realities. Space is not a gentle ocean that carries life from shore to shore. It is a vacuum of lethal radiation and extremes. Ultraviolet rays from the sun can tear apart DNA. Cosmic rays can punch through cell walls, shattering molecules. Even inside a meteorite, any organism would endure acceleration shocks, searing heat upon impact ejection, and eons of freeze-dried dormancy. Laboratory experiments show that some spores and tardigrades can survive short exposures to space, but millions of years is a different story. The odds that a living microbe could remain dormant through such a journey and then revive on Earth are extremely low. Moreover, if life truly came from Mars, we must explain why life did not also colonize other bodies struck by similar rocks. Why do we not find life on the Moon or in the atmospheres of Venus? The absence of evidence on those bodies suggests that panspermia is rare. Recent experiments provide nuance. Researchers simulated Martian conditions by embedding amino acids from simple bacteria into pure ice and exposing them to radiation for timescales of tens of millions of years. They discovered that a fraction of those molecules persisted even after prolonged bombardment. When mixed with soil or rock, organic compounds degraded more quickly, but within pure ice, they were shielded, frozen in time. This suggests that if life ever existed near the surface of Mars, buried in ice, traces of it could remain intact for tens of millions of years. However, preserving amino acids is not the same as preserving living cells. Proteins and nucleic acids are delicate. Their survival does not guarantee that a microbe could be revived. Yet these findings guide scientists to drill into Martian ice rather than into rock, because ice is a better time capsule. Another blow to the Martian origin theory comes from our own fossil record. Evidence shows that life was present on Earth as far back as it could have been, almost immediately after the planet cooled enough to sustain liquid water. Microscopic fossils and isotopic signatures appear in rocks that formed only a few 100 million years after Earth's formation. These timestamps suggest that life began here as soon as conditions allowed. If life had to travel from Mars, there would be a delay in appearance. Furthermore, the chemical composition of ancient ocean sediments matches the conditions one would expect for the emergence of life. The soup of salts, metals, and organic molecules is akin to the interior of a primitive cell. This congruence implies that our planet's own environment was the crucible in which life assembled itself. At this point, you might think the ride is over and the myth is dead. Not quite. Science is not content with simple dismissal. It pushes further, exploring the what-ifs with rigorous models. A recent climate simulation funded by NASA extended the window during which Mars might have had Earth-like conditions. Previous theories held that Mars had a warm and wet period early on, but that it was brief. New models that couple three-dimensional atmosphere and ocean dynamics suggest that the northern hemisphere of Mars could have harbored a stable ocean and rainfall for hundreds of millions of years longer than previously thought. Under a thicker atmosphere rich in carbon dioxide and a small fraction of hydrogen, Mars's northern lowlands could remain warm enough to sustain liquid water, even if average temperatures elsewhere remained below freezing. Glaciers may have flowed from highlands to the ocean, and precipitation cycles could have persisted. This extended clement period provides a greater window for life to originate or take hold. But even an extended window eventually closes. Mars lost its magnetic field, its atmosphere thinned, and its surface water evaporated or froze. If life began there, it would face increasing difficulty surviving. If the birth of life required an almost impossible sequence of events on a single world, does that make our existence more precious or more accidental? Share your thoughts below. Now the roller coaster climbs again, but this time it reveals a view far grander than any conspiracy. Whether life came from Mars or arose on Earth. It is a fact that everything living shares a deeper origin in the heart of stars. The carbon in your bones, the oxygen in your lungs, the iron in your blood were forged in dying suns billions of years ago and sprayed across the galaxy in violent supernovae. Those atoms drifted through interstellar clouds, condensed into a protoplanetary disk, and became the building blocks of Earth and Mars alike. In that sense, you are already an extraterrestrial. You are made of cosmic debris shaped into consciousness. The idea that you could be a Martian is less outrageous than the reality that you are a star-born being. This truth is both humbling and exhilarating. It means that the cosmos is not out there, but inside you. It means that the molecules that encode your memories once vibrated within distant suns and swirling nebulae. It means that the universe has a way of becoming aware of itself. Consider the chain of events that led to this moment. Quantum fluctuations in the early universe seeded galaxies. Gravity pulled gas clouds together, igniting stars that fused light elements into heavier ones. Those stars exploded, scattering elements that would one day become part of your body. Planets formed from rotating disks of dust and ice, locked into orbits by conservation of angular momentum. On at least one of those planets, complex chemistry began weaving molecules that could copy themselves. Those molecules slowly evolved into cells, then into multicellular organisms, and eventually into minds that can ask why. At each step, thermodynamics and probability played a role. Entropy demanded that order be maintained only through the expenditure of energy. Life is a delicate balance between order and disorder. Tiny random mutations in genetic codes gave rise to new traits. The mathematics of probability determined which would persist. Quantum mechanics underlies the behavior of the electrons in chemical bonds, setting the stage for complexity. Cosmology describes the expansion of space and the cooling of the universe, creating the conditions where chemistry and biology could flourish. All of these processes are far more wondrous than any story of aliens tinkering with DNA. If you could travel backward along every branch of your ancestry, not just to the first human, but to the first cell and beyond, would you still see yourself as an individual? Let me know in the comments. Some scientists have entertained directed panspermia as a theoretical possibility. Francis Crick and Leslie Orgel, brilliant minds behind the discovery of DNA's structure and pioneers of molecular biology, once speculated that a far advanced civilization could seed life intentionally across the cosmos. They did not propose that as truth, but as a thought experiment to highlight the difficulty of explaining life's origin. If we ever reached a technological level where we could send self-reproducing organisms to other worlds, would we do so? Would that be a gift or an act of cosmic arrogance? Would we create new ecologies or commit unintentional acts of ecological destruction? These questions are not science fiction alone. They force us to examine our responsibilities as beings who can alter worlds. Returning to Earth's own story, we see that life evolved through a series of bottlenecks and catastrophes. Our planet's early environment was far from paradise. The young Earth endured bombardments by asteroids and comets that could have boiled away oceans and sterilized surfaces. Volcanoes spewed toxic gases into the sky. And yet, life took hold and persisted. Perhaps it originated in hydrothermal vents where mineral-rich fluids created natural chemical gradients. Perhaps it arose in tidal pools where cycles of drying and wetting concentrated organic molecules. Wherever it happened, the environment must have provided both energy and stability for prebiotic chemistry. The fact that life emerged so quickly after Earth cooled suggests that given the right conditions, life is a natural outcome of physics and chemistry rather than a cosmic accident. If Mars once hosted similar conditions, then life might have arisen there too, but we have yet to find definitive evidence. Our search for answers is not purely philosophical. Robotic explorers have been combing the Martian surface for decades, analyzing rocks, scanning for organic molecules, and looking for patterns that could indicate biological activity. The rovers, Spirit and Opportunity, discovered signs of ancient water. Curiosity found complex organic molecules in the soil, though not necessarily biological in origin. Perseverance is drilling core samples that one day may be returned to Earth for analysis. Orbiters have mapped mineral deposits and detected methane in the atmosphere that might be produced by geology or microbes. Each piece of evidence is a clue, but none is yet conclusive. As we refine our instruments and launch missions to Mars, Europa, Enceladus, and beyond, we will inch closer to understanding whether life is a universal phenomenon or an anomaly. In the end, Whether life on Earth was seeded by Martian rocks or arose spontaneously in Earth's oceans may be less important than what life does with the knowledge of its origins. We are a species that asks questions about our own beginnings, that looks to the night sky and wonders if somewhere in that blackness there are other eyes looking back. We are the universe contemplating itself, a brief flicker of awareness in a vast, cold, indifferent expanse. This awareness is our gift and our burden. If we are Martians, then we are also Earthlings, and, more profoundly, we are children of the cosmos. Every discovery we make about Mars, about the early universe, about quantum fields and probability waves, draws us further into understanding the tapestry of existence. And every myth we spin, every conspiracy we entertain, is a reflection of our hunger to find meaning in the unknown. As the ride slows, and you emerge from the tunnels of speculation and science, you might feel dizzy. The idea that you could be a Martian may have seemed terrifying or thrilling. The scientific explanations may have seemed dry at first, but ultimately revealed a beauty deeper than any myth. The truth is that reality is stranger than fiction. We live on a planet where life arose from a dance of molecules, where continents drift and collide, where species emerge and vanish, where a primate species can look beyond its world and ask about origins. Maybe life is rare, and we are a cosmic fluke. Maybe life is common, and our galaxy teems with beings pondering their own stories. Either way, when you look up at the red planet, know that you are looking at a mirror. Not because you are literally from there, but because both worlds are made of the same stardust, forged in the same crucible, shaped by the same physics. Our connection to Mars is not defined by fossils inside meteorites, but by the universal processes that give rise to planets and life. Remember this as you turn off your light tonight. You are part of a story that spans billions of years and countless worlds. Sleep well if you can, knowing that the universe is vaster and more mysterious than any bedtime story, and that tomorrow brings more questions, more discoveries, and more wonder. Cast your mind back to a time when the solar system was young and chaotic. On Mars, volcanoes belched clouds of gas and ash into an atmosphere thicker than anything you see there today. Rains fell for thousands upon thousands of years, carving channels that still snake across the surface. Rivers merged into deltas, depositing sediments in shallow seas. Winds swept across vast plains, sculpting dunes and depositing layers of dust. The polar caps waxed and waned, leaving behind strata of ice and rock. Mars possessed not only liquid water but also perhaps hydrothermal systems where heat from the planet's interior warmed underground aquifers. Such systems could have provided energy and minerals to budding life, analogous to the hydrothermal vents found in Earth's oceans. If you stood on ancient Mars, you might have seen distant thunderstorms flashing above a copper horizon and heard the gentle lapping of waves against a rocky shore. It is no wonder that the planet holds such fascination. It once held everything we think is necessary for life. Compare that Martian idyll to the violence of early Earth. Our planet endured an epoch known as the Late Heavy Bombardment, when giant asteroids bombarded the surface. The impacts were so intense that oceans vaporized and recondensed repeatedly. The atmosphere was thick with carbon dioxide, methane, and sulfurous fumes. Lightning cracked across perpetual storms, striking vast primordial seas. Land was scarce, a scattering of volcanic islands protruding through the endless water. Life would have had to cling to these islands or flourish in the darkness of deep-sea vents. In such conditions, the minerals that facilitated prebiotic chemistry would have been diluted or chemically unavailable. Early Mars, by contrast, offered dry basins where evaporation concentrated salts and minerals, providing natural laboratories for complex reactions. It also had a protective magnetic field for longer, shielding its surface from harmful solar radiation. The contrast between a deluge world and a desert world underscores how different paths might lead to life. The paradoxes that plague origin of life research are worth dwelling on. The tar paradox suggests that if you simply pour energy into a mix of organic molecules, they are more likely to form intractable goo than self-replicating strands. Ultraviolet light and heat drive reactions that produce complex but lifeless polymers that accumulate and solidify. For life to emerge, there must be a way to avoid this sticky fate. Borate minerals, by stabilizing simple sugars, prevent them from collapsing into tars. Meanwhile, the water paradox points out that while life needs water, too much water dissolves and hydrolyzes the bonds that hold genetic polymers together. It is in environments that are alternately wet and dry that chains of nucleotides can lengthen and fold. Mars's intermittent lakes, ponds, and evaporating seas could have provided exactly such cycles, whereas Earth's global ocean might have been too uniform. These paradoxes remind us that the origin of life is not about one ingredient, but about the interplay of many factors in just the right proportions. No discussion of Martian origins would be complete without revisiting the meteorite that sparked decades of debate. In the mid-1990s, a small rock from Antarctica, labeled Allen Hills 84001, captured the world's imagination. Scientists working at NASA announced that they had found tiny structures inside the meteorite that resembled fossilized bacteria. They also detected organic molecules and mineral formations that, on Earth, often accompany microbial life. The story spread like wildfire. For a brief moment, headlines declared that we were not alone, and that life had been discovered from Mars. Even the President of the United States gave a speech about the possible discovery. But science is a self-correcting process. Subsequent analyses showed that the structures could be formed by abiotic processes, the organic molecules could be contamination, and the minerals could have crystallized without biological assistance. What began as a tantalizing hint became a cautionary tale about wishful thinking. The meteorite remains important because it proves that rocks travel from Mars to Earth and that they can preserve complex chemistry, but it does not prove that those chemicals were arranged by living things. Suppose, however, that the directed panspermia scenario were real. Imagine an advanced civilization faced with the imminent death of its star or planet. Unable to migrate en masse, it decides to send its genetic heritage to the cosmos in hopes that life will take root elsewhere. Perhaps they send billions of tiny probes, each containing dormant microbes and instructions encoded in molecular patterns. They aim these probes at young planetary systems, hoping some will survive the journey. Would that act be altruistic, selfish, or simply a desperate gamble for immortality? We can empathize because humans are already contemplating sending capsules containing DNA, music, and art into interstellar space. If we were to seed another world with life, would we feel responsible for how it evolves? Could we be accused of playing God? These ethical questions stretch our sense of responsibility beyond our planet and force us to consider our role in cosmic ecology. The climate simulations that breathe new life into the Mars hypothesis are complex and illuminating. They show that the northern plains of Mars could have held an ocean as large as Earth's Arctic Ocean, rimmed by icy shores and dotted with islands. Above this ocean, clouds would have formed and drifted south, dropping rain and snow on the highlands. Glaciers would have crept slowly toward the sea, carrying with them sediments and nutrients. The interaction between atmosphere and ocean would have created currents that moved heat around the planet, preventing the ocean from freezing completely, even if global temperatures were below the freezing point of water. A key ingredient in these models is hydrogen gas, which when mixed with carbon dioxide acts as a greenhouse blanket. Volcanic eruptions or meteor impacts could have released hydrogen, temporarily warming the planet. Over time, however, the hydrogen would escape to space. The greenhouse effect would wane, and the water would retreat or freeze. This narrative of rise and fall underscores the fragility of habitable conditions on small planets. Looking beyond Mars and Earth, consider that our galaxy contains hundreds of billions of stars, each with its own collection of planets. Some stars are like the Sun, others are giants or dwarfs. Around these stars in dusty disks, planets coagulate, migrating inward or outward, colliding and accreting. In some systems, giant planets migrate so close to their stars that they disrupt the orbits of smaller worlds. In others, planets remain in stable, temperate zones for billions of years. Our own solar system is the result of countless cosmic coincidences. Jupiter's massive gravity shielding Earth from excessive impacts, our moon stabilizing Earth's axial tilt, the presence of water bearing asteroids delivering oceans to our surface. If any one of these factors were different, life might not have arisen here. The same may be true for Mars. Without a strong magnetic field, solar winds stripped away its atmosphere. Without plate tectonics, its interior cooled quickly. And yet, for a time, it may have been a second cradle. The physics that underpins these stories is stranger than science fiction. At the quantum level, particles behave like waves, existing in multiple states simultaneously until observed. This weirdness allows electrons to tunnel through barriers, enabling nuclear fusion in stars and the chemical reactions that power life. Quantum uncertainty makes the timing of radioactive decay unpredictable, influencing the heat inside planets. Probability governs the outcomes of genetic mutations, the formation of clouds, and the orbits of comets. We are the products of countless random events filtered by deterministic laws. The arrow of time, rooted in the second law of thermodynamics, means that energy disperses and entropy increases. Life can only persist by creating local pockets of order at the expense of its surroundings. Understanding this interplay of chance and necessity reveals that our existence is neither wholly random nor entirely predetermined. It is the result of a universe that is lawful yet rich with possibilities. As you watch this from the comfort of your home, metal explorers are traversing alien landscapes on our behalf. The European Space Agency's ExoMars rover, once it launches, will drill beneath the surface to look for preserved organic molecules. China's Zhurong rover has been exploring the Utopia Planitia region, analyzing rocks that may be remnants of an ancient ocean basin. NASA's Perseverance rover is collecting samples that will be retrieved by future missions and flown back to Earth for detailed analysis. Orbiters like Mars Reconnaissance Orbiter, MAVEN, and Tianwen mapping instruments continue to gather data on atmospheric loss and surface mineralogy. Together, these missions represent humanity's collective curiosity. If any of them finds conclusive evidence of past or present life on Mars, it would be one of the most profound discoveries in history. It would confirm that life is not unique to Earth, and that biology can emerge more than once in a single solar system. If they find nothing, that result is equally important, for it suggests that even with the right ingredients and conditions, life may still be a rare miracle. The conversation about life on Mars inevitably leads to questions about the future. Humans are planning to become an interplanetary species. Private companies and space agencies are building rockets and habitats with the goal of sending people to live on Mars within this century. If we go, we will not only be visitors but potential colonizers, carrying with us microbial ecosystems from Earth. This raises ethical concerns. We must ask whether we have the right to alter Mars irreversibly. If Mars harbors dormant life, our presence could destroy it or contaminate it beyond recognition. If Mars is sterile, terraforming it could create a second home for humanity, but at the cost of transforming a pristine world. When we discuss whether life came from Mars, we also implicitly ask what life will do to Mars in the future. Will we become the Martians our ancestors only imagined? There is a deeply personal dimension to these questions. Humans derive meaning from stories about origins. Religions, myths, and science all provide frameworks for understanding who we are and where we come from. The possibility of a Martian origin story taps into our desire to find uniqueness in the vastness. If we are Martians, then we are forever immigrants, carrying the memory of another world within us. If we are Earthlings, then we are the product of this planet's own alchemy. In reality, we are both less and more. Less, because our origin story is not the tale of deliberate design by ancient aliens. More, because our heritage encompasses the entire universe. Your sense of home need not be confined to a single world. Home can be the thin biosphere of Earth, the red deserts of Mars, the cosmic web of galaxies, or the interconnectedness of all matter and energy. Embracing this broader identity can foster humility and responsibility. When the lights are off and the video ends, you might lie awake thinking about red rocks, ancient oceans, and tiny microbes hitching rides on cosmic debris. You might feel small, and that feeling is appropriate. The universe is almost incomprehensibly vast and indifferent. And yet, the fact that you can comprehend any of it is extraordinary. The molecules in your brain have arranged themselves in such a way that you can reflect on their own origins. This self-awareness is a kind of miracle that does not require supernatural explanations. It arises naturally when complex systems have enough time and energy to organize. Thinking about a Martian origin for life is less about proving a theory and more about confronting the boundaries of our knowledge. It encourages curiosity, skepticism, and wonder. Whatever the truth, the search itself enriches us. The story is not over. Every rover wheel that turns, every telescope that peers into the dark, every lab experiment that simulates ancient conditions adds a chapter. And as long as we keep asking, we remain part of the cosmic conversation. What about the soup that simmered on early Earth? Scientists imagine shallow pools heated by volcanic activity, where simple molecules could undergo cycles of evaporation and condensation. In these settings, fatty acids might have formed membranes, enclosing strands of RNA and creating the first protocells. Hydrothermal vents on the ocean floor offered a different cradle, cracks in the crust where mineral-rich water mixed with seawater, creating natural proton gradients that could power primitive metabolism. Iron sulfide minerals in these vents could have catalyzed reactions, building more complex molecules from simple gases. Lightning in the atmosphere may have sparked reactions that produced amino acids, which then rained down into the oceans. Even meteorites themselves delivered organic molecules, adding to the molecular diversity. All of these processes illustrate how the environment shapes chemistry and how life emerges not from a single magical ingredient, but from a network of reactions sustained over time. Once life began, evolution took its own roller coaster ride. For billions of years, life on Earth existed only as single-celled organisms. These cells diversified into bacteria and archaea, mastered photosynthesis, and changed the composition of the atmosphere. At some point, one cell engulfed another, and instead of digesting it, they formed a symbiosis. This event, known as endosymbiosis, gave rise to the eukaryotic cell, which contains organelles like mitochondria and chloroplasts. It was a profound leap, allowing for greater complexity. Later, cells began to adhere and communicate, forming the first multicellular organisms. These organisms evolved specialized tissues and organs, eventually giving rise to animals, plants, and fungi. The Cambrian explosion saw an unprecedented diversification of body plans. Fish crawled onto land, reptiles gave rise to mammals and birds, and some primates developed large brains capable of abstract thought. At each stage, randomness and necessity intertwined. Had conditions been slightly different? Had an asteroid not wiped out the dinosaurs? Had climate shifts not occurred? Humans might never have evolved. Panspermia, if it occurs, is not a one-way street. Rocks have been ejected from Earth as well, and some of them may have landed on Mars. Large impacts on Earth can fling debris beyond our gravitational grasp. Microbes embedded in that debris could, in theory, survive the journey if they were shielded. This raises the intriguing possibility that if Mars did harbor life, it might have been contaminated by Earth, or vice versa. In fact, interplanetary exchange of material happens more often between neighboring planets than previously thought. It is estimated that over the lifetime of the solar system, millions of kilograms of rock have traveled from Mars to Earth and from Earth to Mars. Within that flux of material, there could have been countless opportunities for hitchhiking microbes. Yet because we have no evidence of life on Mars, it seems either that life never gained a foothold there, or that transferred life did not survive. We may have been both potential recipients and donors of life, emphasizing how interconnected planetary bodies can be. Philosophically, the thought that life might be mobile across worlds challenges our sense of belonging. Do we belong to Earth because we evolved here, or to the cosmos because our atoms were forged there? Does the possibility that we are Martians diminish our connection to our planet, or does it enrich it by showing how deep the roots of life can go? Identity is more than geography. It is the stories we tell ourselves and the meaning we derive from them. Science gives us a story that is evolving and open-ended. It invites us to be part of a universe that is far stranger and more beautiful than anything our ancestors imagined. It asks us to find significance not in ancient myths, but in the processes that build stars, assemble molecules, and give rise to minds. Knowing this, perhaps we can approach debates about life on Mars with humility and wonder, embracing uncertainty as a space for growth. As we close our eyes and imagine the red planet, we are reminded that stories of origin are never simple. They twist through time like the channels on Mars, carrying sediments of fact and layers of speculation. The truth may be that life is resilient and opportunistic, willing to arise wherever conditions allow, whether on a wet blue world or a dry red one. Or it may be that life is exquisitely rare, the outcome of a cosmic alignment that will not repeat. Either scenario fills the heart with awe. There is poetry in the idea that we are cousins of Martian microbes that never made it, and there is poetry in the idea that we are unique in a silent universe. Holding both possibilities in your mind is an exercise in wonder.